Next, let's move on to dynamic arrays, which are much more common and much more useful than static arrays. You've probably already used a dynamic array, you just might not have known it. In Python and JavaScript, dynamic arrays are the default. In Java, you can use an array list, or in C++, you can use a vector. So let's remember that the problem we're trying to solve here is the fixed size problem. Our static array is a fixed size, but what if we have an array that is dynamic in this case? Now, when we were creating static arrays, we usually have to specify the size. So when we were using static arrays before of size 3, we specified that it was size 3 when we created that array. But in this case, let's say this is a dynamic array and we created a dynamic array, but we didn't initialize any of the values. And with dynamic arrays, you don't necessarily have to specify the size. If you don't specify the size, usually it'll initialize it to some default size. For example, in Java, I think usually the default size of an array list is 10, but that number could be arbitrary and it's not necessarily important. Let's say we initialized a default empty dynamic array. Let's just say it got initialized to size 3 in this case. While the size is 3, the length of the array is actually 0 in this case. We have nothing added to it yet, so we say the length is 0. Now, as we add elements to the end of the array, we call that pushing to the array. So we're pushing to the end of the array. We pushed a 0 to the array. Now we're going to push another element, and what that means is insert it at the next empty spot. So let's push a 4 in this spot. Now with the internal implementation of this dynamic array, it will maintain a pointer, or basically a variable telling us what index is the last element of this array. So we know that the first element is at index 0, the next element is at index 1, and we know this is the last element so far. So we have a pointer telling us that this is where the last element is. We can also use this pointer to get the length of the array. So right now this pointer is at index 1. That means the length of the array must be 2, because remember we're starting at 0. So we talked about pushing, but we can also pop values. Popping in this case also refers to the end. So that's why this end pointer is important for us. We're going to pop the last value. Just like how pushing a value to the end is an O of 1 time operation, popping a value from the end is also a big O of 1 time operation, because we know exactly where that value is because we have that pointer to the last element. We pop it, and we also want to now take this pointer and then shift it to the left by 1. So now we're maintaining that this is the new end of our array. We could also pop this value as well, which would make our array be basically of length 0 again. But that's the main idea. Now for the problem we're trying to solve, let's push another element. Let's push a 7. Now this is the end of our array. Now let's push another value. Let's say I want to push a 9. Well, we ran out of space. So what is our dynamic array going to do? So far in memory over here, we have a 0, a 4, and a 7. We previously talked about why we can't just allocate more memory right next to it. So what are we going to do? Well, we're just going to allocate a brand new array that will be able to contain all of the elements that we're trying to store. What I've done here, though, is taken the original capacity, the original size, which was 3, and multiplied that by 2. So now we have an array of size 6 rather than size 3. We're only inserting one extra element though, so it would have been sufficient to just have an array of size 4. So why did I double it? Well, we'll get to that in a minute. So since we allocated a brand new array, we know it's going to go somewhere in memory, somewhere random, but we don't really care where it is. Of course, it has to be a different location than where our first array is, because this is still in memory so far. And what we're going to do is take all of the original values stored in the array, so over here, and we're going to copy them into the second array starting at the beginning. So if this is at index 0, well, it's going to get copied to index 0 in the second array. If this is at index 1, it's going to get copied to index 1. If this is at index 2, it's going to get copied to index 2. So our second array is going to look like 0, 4, 7. So you can tell we solved the problem of not having enough space. Now we definitely have enough space for this 9 to now also be here. So now our memory looks correct. We have all the values that we wanted, but the problem is we still have the original array. Do we really need this anymore? No, it's just taking up space, but we have all the values in the second array anyway. So now at this point, we deallocate this. We free this memory. We basically tell the operating system we're not using this anymore. You can use it to allocate different variables if you need to. So this doesn't exist anymore. So this definitely allows us to get around the fixed size property. So now if we add even more values to our array, which replaces the original array, we can keep doing that. Let's add a 10. Let's add an 11. Let's add a 12. If we add a 12, we're going to do the exact same thing that we did before because we ran out of space. Now it's time to allocate a new array, and we're going to make one that's double the length of the original one. So size 12, and then we're going to insert the new element, and we'll have a bunch of extra space to add more elements if we need to, but we might not need to. Now let's get back to one of the questions before. Why did we double this rather than just increasing it by 1 for the space that we needed for the original element? Well, notice how since we allocated a brand new array, we basically did a big O of n operation, because first allocating the memory itself takes a big O of n, where n is the size of the memory that we allocated. But regardless of that, we also had to take the original values from the original array and then move them into the second array. We had to push every single value. So that was also big O of n, where let's say n is the length of the array, meaning the actual values that exist in the array. But what we're used to is pushing a value to the end of an array. In this case, let's say we push a value here, 10, that would have been big O of 1. So what we notice is if we run out of space, yes, we can still add the next value, but it takes extra time because we have to create a brand new array, push all the original values into it, which is big O of n time complexity. That's the reason why when we create a bigger array, we are doubling the capacity every single time. We're not just increasing it by 1, because we're finding a middle ground between not having to allocate a brand new array every single time, but also we don't want to have a bunch of empty space. We could have just created a super large array with a bunch of empty space, right? Like 90% of it could have been empty space, but that wouldn't have necessarily been good because then we're taking up a bunch of memory from our operating system. And if we do it this way, where we double the capacity, we get something called amortized complexity, amortized time complexity. And what that basically means is, yes, it took big O of n to add an element if we ran out of space, but we know it's going to be pretty infrequent when we run out of space. So we can still say that the amortized time complexity of pushing a value to a dynamic array is going to be big O of 1. You can think of it as being the average time, because we know on average it's usually going to be big O of 1, not big O of n, because it's the vast majority of the time we add elements, it's going to be constant time, not big O of n. And there's actually a mathematical proof for why this is the case. In math, it has to do with power series, and I won't go too in depth into the math, but I will give you a high-level explanation for why this is true. Let's say our goal is to push 8 elements into a dynamic array. Maybe the default dynamic array was only of size 1 when we allocated it. So let's say we add our first number 5 to the array, and so far we have an array that looks like this. Next, we want to add a 6 to the array, but we know we don't have space. So what we really have to do is take this 5, move it down to here, and then insert the 6 over here. So I'm just counting the operations we're doing so far. We did one operation when we added this 5 here, and then to add the 6, we actually had to do 2 operations where we moved the 5 and then added the 6. Next, let's add the number 7. But for us to do that, we have to allocate a new array. And since we're doubling it every time, this array is of size 4. So we're going to move the 5 here, we're going to move the 6 here, and we're going to add the 7 here. So while we did 3 operations, we inserted 3 values here, allocating the array itself actually also took time complexity. So allocating an array of size 4 took 4 operations, we can say. And we're going to continue to do this. I'm going to add an 8 over here. That's perfectly fine. We're going to add a 9 here. We know that's going to require shifting all of these. And then let's say I add a 10, an 11, and a 12, which we do have space for here. So let's say it took us an additional 8 operations to actually build this one. Now I'm oversimplifying a little bit because it actually took 8 operations to allocate the space, and then it took another 8 operations to actually move each value into the array. But we're going to ignore that just for now. The main point I'm trying to get at though is to create an array of length 8, it actually took us 8 plus 4 plus 2 plus 1 operations. But since we're doubling this every single time, this calculation is always dominated by the last term. What that means is the last term is always going to be greater than or equal to the sum of all previous terms. This is a math concept. And this is the reason why we're doubling it rather than just increasing it by 1. But why is this actually important? Well, to create an array of size 8, let's say in this case it took us 15 operations. We know that this number is dominated by the last term, which means that it's always going to be less than or equal to 2 times the last term. In this case, the last term is 8, but we know in the general case that it's going to be n for how many elements we wanted to push to an array. So we say that this is 2 times n. So in big O terms, we would say it's 2 times n. But with big O notation, we never care about constants when they're multiplying a variable. In this case, 2 times n can be simplified to be big O of n. We don't really care about constant values, at least when they're used in multiplication or addition. So finally, the result that we arrived at is pushing an arbitrary number of values to an array is big O of n time overall, even though sometimes when we have to exceed the capacity, we have to shift a bunch of values. But overall, it reduces to be big O of n, which is pretty much the same that we expected from our static arrays. So as long as we double the size every time that it's exceeded, we do have an efficient data structure when we use dynamic arrays. By the way, let me illustrate to you why we don't care about constants when we're talking about big O time complexity. We don't care about the difference between big O of 2 times n or the big O of n. We don't care about any constant c that could be there. Any constant, no matter how big it is. It could be 10, it could be 100, it could be 1,000. We don't care about it. And again, it's because of math. Suppose this line is representing our n line. As the input size grows, the runtime is also going to grow, but it's growing linearly, right? It's a straight line. But if we had a runtime complexity of n squared, now this is a 2, but this isn't the type of constant I'm talking about because this is being raised to a power of 2. It's not being multiplied by 2. Powers are definitely important, but we don't care about, some constant multiplied by n, and we don't care about some constant added to n. It could be a different constant than this one, but we don't care about it if it's added or multiplied. As you can see, n squared grows much more quickly than n, and that's the idea. Now for some smaller inputs, it might matter. Now with these, they do intersect at input size n equals 1. But suppose we had a constant here. Maybe we actually have a line like 2 times n. It doesn't matter what the constant is because they are definitely going to intersect at some point, and probably in this case it'll probably intersect at 1.4 or something like that. But the idea is they're going to intersect at some point, and after that point of intersection, the larger growing function is always going to be greater than the slower growing function. And that's what we care about. We don't care about small inputs like 1, 2, 8, even 100, or even 1,000. We don't care about these small input sizes. We care about really, really big input sizes because those are the ones that slow down our CPU when we run programs. That's why when we talk about big O time complexity, we don't care about constants. We care about how quickly is it growing. Is it big O of n or is it big O of n squared? The same would be true if we added a constant. For example, this is what n plus 8 would look like. Well, it gets a head start over the quicker growing function, but at some point they're going to intersect, and at that point, the quicker growing one is going to grow way faster. It's going to go off the charts, while this one still grows at the same rate. Now, to summarize, the time complexity for dynamic arrays is essentially the same as static arrays. We can still access the ith element anywhere in constant time. We can push and pop elements at the end also in constant time. Even though in some cases we might have to resize the array, we still basically assume that it's a constant time operation for the reasons that I talked about earlier. And the good thing about dynamic arrays is we can do so even if we don't have space, because yes, we can allocate more space. The downside though is inserting into the middle or removing from the middle is still going to be a big O of n time operation, because we're going to have to shift every value over. And there's no amortization for this. In the worst case, this is always a big O of n time operation. So now that we understand dynamic arrays, the next thing for us to do is understand how we can use them.